All right, guys, I just recently swapped out a PMD again because it was failing. And I'm using the gray type from Stanadyne, which they call the Bulletproof 39405. These are mounted on mine remotely inside the bumper. We can see the new ones back on the aluminum finned heatsink here. It's right inside here, right behind the front license plate. Even in this position, I only get about 3 years, maybe three in a few months, 3.5 tops, even in this position here in the front, and they go out. Now, there are some failures on these that can be repaired. And part of what I'm going to show you in this video is how we can open these guys up and take out these transistors and get it to a point where we can inspect and repair some of the common types of failures that might occur. One has to do with how tight these transistors are in their positions. One has to do with whether those transistors have been shorted out or damaged from heat, which is a common occurrence. And the other is whether the solder joints in these positions have cracked and come loose and broken the circuit. So those are 3 things that can be fixed on these, but that's about it. But it's worth a shot. They quit making these in 2015, and right now they're just selling through the old stock. So let's get to it. All right, guys, the first step to working on this is to get this cover off. And on these gray models, there's a couple of places that are somewhat indented that you could do that. Particularly right here on this edge down here, you can get a small flat-bladed screwdriver in here, and you can work it in and begin to pry the cover off. The cover is just sitting on top of the potting material or conformant coating, whatever kind of term you prefer, that they put in on this during assembly. Sometimes it helps to have a couple other tools just to kind of wedge it up under there while you're working on it. All you're trying to do is kind of break this guy free that they pressed on while this material was still wet. Just want to have some patience, go slow, steady prizing, and it will let go. All right, so there's that. You can see this is the potting material, conformant coating that's put on the board during the manufacturing process. It's quite hard. It's like a 2-part epoxy plus maybe even some type of silica mixed in. Fairly resistant to all sorts of chemicals that you might have access to. Certainly nothing DIY that you're going to have. There's a couple of chemicals that you might have for conformal coating removal if you're in a lab environment, but they're not something you typically have in your garage, so I'm not going to mention them. The method we're going to use to get this broken down is heat. And this particular material, in my experience, will give way with a hot air gun. It basically fragments and shatters, turns into dust, and that's how we remove it. Let me remove these thermaloy covers. Now, these gray ones don't come with these anymore. They came with the original ones, and I still use them because the purpose of these, this has nothing to do with heat. Nothing at all. These are designed to be electrically insulative and thermally conductive. And the purpose of these things is to prevent these 2 transistors from grounding out. If they were to ground out, they would be destroyed on the vehicle's ground. So that is something that's very important to have there. There's all air under here, sealed against a heat sink. There's nothing that's going to conduct there, so it's best to have them on. The next thing we're going to do now is begin to locate where the things that we have to remove the conformal coating of are. And what I like to do from past experience, I've got my little cheat sheet here. I know the location of the 2 Phillips screws that are used to hold this into position. On the other side, the studs that have the nuts, right? So these 2 screws here would correspond to what we see here with these nuts in these positions here, here, and here. There's 2 pins that come out of this particular old 1970s style transistor. This is an MJ15004. The modern versions have a G suffix, but the original ones from Motorola in the early 1970s did not. They're still made by On Semiconductor, so you can still get them. They're popular in audio amplifiers and equipment like that. But so they're not anything that's hard to come by. I measured these off in tenths, right? So 8.5 tenths in on either side for these screws, 6.5 tenths down, 7 tenths up. That'll position us where the screws are. The two pins that are soldered in are located on this side, 6.5 tenths in, 6.5 tenths in, 11 tenths in, 11 tenths in. So they're all pretty much equidistant. The only difference is since these transistors are mounted in opposing directions, right? So you can see by the writing here, this writing here is upside down, this writing here is correct and legible. That's because they're flipped in the circuit. And so that causes us to have the situation where the distance from the bottom on the ones on the left-hand side, looking top down, are 12 tenths of, and then the ones on the right are 13 tenths. So all I'm going to do at this point is grab myself my ruler in tenths, and I'm going to go identify where all this stuff is, right? So I'm going to come over at 6.5 tenths, and then I'm going to come down and mark these off. So 6.5 tenths, and then 8.5 tenths in puts me right here. I'm just going to make a little mark there, and you can kind of see it where the material has settled with an air pocket. Makes sense that right around here would be, and you can kind of see the outline of your Phillips head screw. You can kind of see the outline of your Phillips head screw here. Right, and so in some cases you don't even need to do these kind of measurements. But again, looking at that one right there, 8.5 tenths in, and then from the bottom, 6.5 tenths, and that puts us right on top of that Phillips head screw right there. So that's the first thing we're going to remove. We're going to fire up the hot air gun. We're going to let it warmed up, and then we're going to come back and get started. All right, guys, I've got this set to 350 degrees, and what I'm going to do is I'm just going to start heating up the area right around the top of this screw here, because this is our weakest point since it's the thinnest. And I'm just going to take a small flathead screwdriver. I'm just going to begin to, and I know there's a lot of shadows here. Let me see if I can do it at a different angle to avoid the shadows. So if I can get another light on here too, it might help. Let's see if that helps. I'm just applying steady pressure while heating, and what you can see is this material starts to shatter. It gets soft and it shatters. Now it does get off some fumes, so I'm only going to do a little bit of it like this to get started. Then I'm going to put my mask on. You guys can watch me do this while I have some protection on here. But I'm just going to do a little bit of it just to show you how easy it fragments under heat. And we can use a little bit more force around this screw because there's no componentry around it. It's fairly robust. See, it's just fragmenting up. And we have to get these things exposed because it's the only way we can be sure we're able to tighten on the nuts when we go put it back together. I'm going to grab a different pick here. And now I'm going to expose the threads, or excuse me, the head of the screw here, because there's some material inside here that you'll want to get out in order to be sure that you can get the screwdriver bit to fit in really well. Now I do have my eye protection on right now because this stuff can fragment and pop up. As you can see, we've already exposed one of the screws. So let me get my protective mask on here, and then I'll take you for a tour, and you guys can watch me expose this one, and then we'll keep going after that. All right, guys, you can see that we are almost done with this side. Got a little bit of fine work to perhaps do, but here's one of our terminals to the transistor. Here's the other terminal of the transistor. We have both of our mounting screws that connect over to these nuts on this side. And this point, that's all we need to do to extract this. Now, we'll do a little bit more work to make sure these screws can freely turn. There's a little bit of this stuff that's kind of holding it to the circuit board that we'll want to get rid of. There's also still a few pieces inside where we want to put the bit of the screwdriver that we want to clear out. But we're at the 90% of the way done with this one. So I'm just going to continue doing what I did here, although switching from the small screwdriver to this pick. And again, just trying to get all the material out so that the screwdriver bites in correctly and that we see the ground ring that sits right around the edge of this particular screw. And even after heating this material up, it remains a little bit weak so that we can continue to do this fine detail work. So it's about another 10 minutes or so of fine detail work. I'll come back and I'll show you the final product of that effort. All right, guys, this is where you should be if you've gone through and continued on like I have. You've got both of these Phillips screws on both sides for the studs exposed, and you've got the solder connections for both transistors exposed. And then to be sure you've cleaned out just enough around them, they should spin freely in each of their unthreaded studs, standoffs that they go through. Right. So at that point, we've done the bare minimum, right? So there's a number of surface mount components right in this area here. And so we don't want to remove this because there's too much of a chance as it peels off, it'll remove one. There's a surface mount component that we can just barely make out right there. Similarly, there's going to be some on this side in between here so we don't want to mess with that. But because of the stress of these screws for the studs, engineers typically don't mount anything near these, so you can be relatively aggressive with it. What you want to do is you want to keep coming down like you saw me do until you can see this ring around the bolt or the screw, which indicates the part that makes contact on the circuit board. And then I've used some cleaner, some electronic board cleaner, just to get the dust off. So at this point, the next thing we're going to do is remove these studs. And we're going to use a 1/4 inch socket for that. Whoops, sorry about that, guys, hit the camera. And this is going to be a two-handed job in most cases. These lock nuts, these nuts rather, are Loctited in place, I should say. And I might not be able to kind of do this on camera because it's a awkward kind of a setup, but you got to break through that old Loctite. You want to be super gentle when doing this because you don't want to slip and hit the board. But at some point you'll feel that the Loctite has given way. And that you have the nut and the lock washer off. At that point, we can take a small brass punch and push this guy through because he's often held in by some of that coating that sinks in, gets down around the teeth, or the threads rather. And we'll have to take a pick and pull all that off as well. But that's one. We're going to go through and do the other three, and then we're going to desolder the transistor and remove it. So guys, as we get the shavings off of the threads of the bolts or the studs, we can see that it's kind of a green color. All right, guys, we're going to start to desolder now. I'm going to be using a vacuum desoldering gun just to hopefully try to speed this up a little bit. Sometimes this is all you need, but because of the heat we might have been applying near here, we could have had solder drip down onto the other side of the board. You never know. What I like to do is stick it in there and wiggle it around just to try and get what might have dripped through. Maybe we'll get lucky. We'll see in just a minute. This kind of tool does is it heats everything up, melts the solder, and then sucks it out with a vacuum. Very handy. Okay, so some of them look clear, some of them don't. Let's see if we can get this guy out. It's going to be a tight fit no matter what, so what I think I'm going to use is a pair of ignition pliers. Because either way, I'm suspecting these are bad. So let's see. This one here looks like it might be okay. It's definitely wiggling. You got to remember too, there's a thermal pad at the bottom here that's going to be kind of holding it against the heat sink. This whole piece here is actually a heat sink. This is a non-conductive type material that is used to conduct the heat that comes off of these transistors nominally into the injection pump. All right, so one of them's loose, one of them's not. Let's see if we can get the other one to move just like the first one. All right, they're both moving. Now we just got to overcome the potting material that has slipped down in between the leads. Just going to work it out. There we go. There's our thermal pad underneath the transistor. And then you can see here, if I zoom in, you can see where the potting material has ran down underneath the circuit board, filled in these cavities here. That's what kind of gripped onto the leads even after they were properly desoldered. So I'm going to remove the other one, and then I'll show you how to clean it up and get started on installing a new one. All right, guys, we've got both of these transistors out. And we've got both of the thermal pads, although I'm not going to reuse these. You can reuse them if you don't damage them. The only reason I'm not going to reuse them is I've gotten something that's far superior to these ones that Stanadyne originally used that I'm going to be using in this repair instead. Next thing I'm going to do is I'm going to take my sharp pick, and what I'm going to do is open up some of that coating that has slipped into these holes, making this a little bigger so we don't have as much trouble installing the new ones. Don't want to go too far in, just enough to get rid of that snugness we had when we were trying to remove it earlier. Ideally, you could also probably heat up a little bit on this side and chip it out, but I don't think that's necessary. It actually is somewhat good in that it's going to perform an insulating function. All right, so at this point we can see through. I think you guys can make that out on the camera. We can see through these, so we've got a clear shot all the way through to the other side. We're going to use some replacements, brand new, matched pair, same part number from On Semiconductor. And all we're going to do before we install these is make sure that they are good. And we are going to do that with a multimeter that has a diode test function. Put it on the diode test. And then what you can do is these are what's called a PNP type transistor. So looking at the data sheet that I have here. So the 15004 is a PNP, and then it has a sister that's an NPN, but we're interested in the 004. We look at the PNP schematic. The case is the collector. It should say collector here. It just says case, but it's collector. Pin 1's the base. Pin 2's the emitter on a PNP. Here's kind of like the orientation and style. Here's the marking diagram so that you can tell what you're reading. I mentioned before that G suffix is just something that's more modern. All it means is it's a lead-free package. Never did have any lead in it, so there's nothing special about that. Location code, year, week, and country that it was manufactured. You know, just taking a look at the one we've got here, we can see this one has MEX on it for Mexico. It has a BM 2046 for the code. And then taking a look at the format here, BM 26, and then the work week is the last two at the end. So we can see here that it's a 2046. So it was made in 2020, and it was on the work week, the 46th work week, right? So 2020 was the manufacturing date, 46th work week. Location code would have been this BM, although it only indicates a 1 here, a single letter. It's obviously changed because here you have 5 characters, and here we have 6 characters. So a little bit of variation, nothing concerning. Diode test, negative on this pin. Touch it, whoops, let's get this over here where you guys can see. Touch it to the collector. We see a voltage readout there. Touch it to the emitter, and we see a readout there. If we were to flip it and put the positive on the base, we should see nothing. When we touch the collector, nothing. When we touch the emitter, that tells us this is a good transistor. I'm going to put a new insulating pad on it. These particular pads that I'm going to be using are the highest rated thermal pads on the market today. Each of these pads cost $5, and that's more. It's almost as much as the transistor itself. But I'm aiming to get longer life out of these, and one of the big problems is getting conductivity from the device to the heatsink. So we're going to put this new pad on this one, and then we're going to do the same thing with the other one. We'll go ahead and test it to make sure it's good. We'll put a pad on that one as well, and then we'll come back and get it installed. All right, guys, we got this cleaned up. We ended up having to get a soft plastic scraper to get some of this residual thermal pad off. We want to have it as smooth as possible for the new pad. Also, I noticed that this coating that had dripped through where the solder pins go had raised the surface slightly, so I took a pick and chipped it out. It didn't heat anything up here. I just chipped it out so that we don't have that bulging anymore. That done, so notice there's a little piece right there. It's pretty brittle. Get a pick in here at the right angle, it kind of chips off, like that piece I just broke right there off. Just want to make sure that everything is nice and smooth. At this point, we can install our new transistors, and they do go in opposing directions, if you recall. So we're going to push that down into position, and then the other one goes in this direction. You can't put them in backwards because of the way the pins on these TO3 type transistor packages are set up. They can only go in one way. And now we can get our studs, put them back in, and then what we'll do is we'll put our green Loctite on the other side to secure them. We've also cleaned up the surface where these make contact. And if we were to go take a continuity test, just to show you something else, get the meter out here. Right, so from here to here has continuity. From here to here has continuity. We could, repeat that diode test in here that we did before. There's also continuity on the collector of both of these. Right, so they're hooked up in that way, and that's one way that you can ensure that you're getting the circuit complete when you tighten these down. So I'm going to go ahead, put a little bit of Loctite on those lock nuts and washers, and put the piece back down together. I'm going to tighten this up just snug until we get them soldered in, and then I'll tell you the torque value. In fact, actually, I won't put the Loctite on until after we get it soldered in. We're just going to put them on now to snug it up so that we can get the solder piece done. Then we'll do the Loctite, and then we'll talk about the torque value. All right, guys, we're at the point where we're going to do the soldering of this. So I'll just take you along for that. Because of the heat sink involved, I'm going to be doing 425 degrees because there's a lot of heat that's going to get sunk off of this. Going to turn our fume extractor on. We just want to make sure we get it good and heated up so that it is a good bond between the terminal and the board. You can see it takes a moment before it gets down there. We also want to make sure it's a heavier coat just because of the thermals involved and the vibrations involved in this particular application. Alright, so these look good. Just going to reheat this guy here just a moment just because he looked a little bit uneven to me. Looks good. Yep, so now at this point, we're ready to release the tension that we had on these fasteners. We just wanted to have them, as you remember, tightened up enough so that we could have good contact for this soldering step. Get that nut out of there. Do this guy. Now the next thing we're going to do is the factory used Loctite. And if you noticed as you were cleaning the threads off of these fasteners, you would have noticed that the color of the material that was on the threads was not black, but green. And that was the Loctite material that was used. Yeah, this guy just gets stuck in there for some reason. All right, well, we'll leave him on there. It's okay for now. So what we're going to use is the same type of material. I'm going to use a Permatex brand, but we're going to use thread locker green. Permatex number 29,000 is the number down here. And that is the appropriate type of material for small fasteners like this. A little bit too much there, but that is okay. Clean it up in a minute. All right, so we got our stuck one off. And then we're going to talk about torque. So obviously there's no specified torque value. These things were not meant to be rebuilt. But I can tell you just from looking at a brand new one out of the box, it's very, very low. Only a few inch-pounds. And I don't have a torque wrench that actually goes that low, so kind of going to use the two-finger method. And I'm just going to twist this with 2 fingers until it feels snug. And once I got this where I can't turn it easily with 2 fingers, I'm done. That should put us in the neighborhood of around 9 to 10 inch-pounds of torque. And that's what we're going to want to do on all 4 of these. So we're going to go ahead and do that, and then we got one more step after we get everything torqued down. All right, guys, now that we've got both of these torqued up, we're going to reinstall our thermaloy covers. Now remember, I mentioned to you that these are actually something that's necessary and shouldn't be removed. I'm going to show you the data sheet on this for its purpose. Just get them snapped in there. You notice there's a little tiny pinhole right at the top of these. Here and here, which can be used with a probe from a test voltmeter, if you're using that to test diode test or something of that nature like we did earlier. All right, so let's take a look at a couple of data sheet items before we move on to the last step. So here's the data sheet for these thermaloy covers. They're made by Avid. They're still made by the same company they were back in the day. And what's key about the data sheet, there's not much to it other than dimensions and some material information. But the key thing is, what is this for? Well, this is designed to prevent accidental electrical shock. But in our case, it's to protect the device from being shocked. Remember earlier in the video, I mentioned that on these transistors, we've got a base and emitter, and the case that's being used to sink the heat is the collector. And we cannot allow the collector to make contact with vehicle ground or it destroys the transistor. That's the purpose of this device, to protect that from happening. The second thing I wanted to show you is I mentioned earlier about the when we put these transistors in, those white adhesive insulators that I used. They're from a company called Parker Cometrix, or Comerix rather, Parker Comerix. And the one I used is this 1671 model, the white. And just wanted to run down some specs on this. The one that is of most interest is this 2.6 value, which I guess if we scroll out just a little bit, we can see that is the thermal conductivity rating. So that 2.6 watts is the highest rated insulator in the TO3 transistor type packaging I could locate, and that's why I went with it. So that should be a very superior type of material than what Stanadyne originally used. So at this point, what's left? Well, it's not just putting the cover back on, guys. We have to re-insulate this. It's not the kind of board that's meant to sit out in the open. And the material that I use for this when doing these rebuilds is this here from MG Chemical. So this is a black flexible potting material. It is designed for the purpose we're going to use it for, but it ends up drying flexible. So you might say, geez, after all the work you did to get this open, why on earth would you put that material back in there? Well, I'm not going to put this material back in there. I'm going to put this material in there. That's going to provide the insulative properties that we need to protect this, and it's also going to be a lot easier to remove when we decide we want to rebuild this again. So this mixes up in a 1-to-1 ratio. It takes about 48 hours, 2 days, guys, before this stuff sets in, unless you heat it up. So typically, you know, it's in the fall now, so the best I could do is set this in a windowsill. I might be able to cut it down to a day. It doesn't matter, you know, I'll leave it sitting in there for a week and then come back and make sure that it is in set up really well. We'll do is we'll fill in all of this first, and then we'll run it along the outside edge as a sealer for the cover, and then we'll just let it sit for a few days. And then the last test that we'll end up doing on this is we won't bother putting a resistor in here. We'll just go ahead and plug it in and make sure that the engine starts. And at that point, I consider these good enough to carry as spares until the new one I have gives out, and then we'll see how this one does. So I'll get this mixed up, and we'll come back and do that step. All right, guys, we've got our batch mixed up here, and we're letting it air out. If we take a look at the instructions, stir part A and B, scrape the bottom to get all the material back in the solution, mix the desired amount by ratio of 1-to-1. What we did was we went with 12.5 cc's and another 12.5 cc's for a total of 25. Mix it gently and then let it stand for 15 minutes to de-air. We're coming up on that in just a few more minutes here. Break the bubbles on top with a mixing paddle. We're using a popsicle stick for that. And then pour into the cavity that you want encapsulated. Let stand for 48 hours. Or if you heat it up, it'll cure even faster, as I mentioned before. Before we do that, already got 3 of these out, but we want to go ahead and clip our leads. Grab one like this, just so it doesn't go flying on you. Got all 4 of those clipped off. And then what I'm going to use, you can see this is a very watery consistency for this material. So I'm just going to use, I keep these old syringes around for the purpose of working with materials like this. And we're just going to come over here and fill it in. Just going to keep doing that until we have everything filled in the way it was. And the reason I made this much is I have actually 2 of these units that I'm going to be doing this for. Now I'm not going to fill in this recessed area, and I'm using my fume extractor because there are some fumes with this material. Then I'm going to take a Q-tip and I'm just going to go around the edge. Going to put our top cover back on. Wipe off the excess around the edges. I'm just going to set this 3-pound hammer on it until it cures. And then we're going to make sure that the cover is well seated and held into place. While that's going, I'm just going to go ahead and start repeating the process on the second one that I have, and we'll come back when it's all cured. All right, guys, I ended up going with one of these clamps for this task, and it worked out really well. I started off with just putting weight on top, but what ends up happening is you get the material seeping through the seams as it's starting to harden up, and something like this is a lot better so it doesn't get anything on it and doesn't get messy. So we've let this sit for a few days now, and it's come out great. Now I'll show you the second one that I had. I didn't put the cover on so you can see what it looks like inside. If we zoom in a little bit here, we can see, or probably just from this angle, right, you can see that the replacement material is much more glossy than the original potting material that Stanadyne used. The original material from Stanadyne has like a, very distinct hard. It's very, very hard and feels almost like it's, got a silica base to it, whereas the replacement material, it's much softer. You can push it in, it's flexible. It'll make it a lot easier to get off. Now, what we sacrificed on this is we get all of the protections of a normal electronic device potting compound, definitely an electronic insulator, but not thermally conductive like what Stanadyne used. But on the other hand, I think it's superior in the sense that it's more flexible to the heat cycling that's going to occur with this particular application in terms of less stress on the solder joints for these two transistors. So the next thing we're going to do is the smoke test, right? So I've got my new one that we put in here that we started off this video on, and I'm going to just remove the plug from the top here. Bring this over, and now we're not going to put a resistor in here. And if you need to know how to do that, I'll link one of my earlier videos for that. The resistors for these gray Stanadynes are unique. It's not compatible physically with any of the previous black ones or any of the aftermarket PMDs. And the wiring harness is also unique, including the extension harness. All right, so all I'm really going to do here, I'm going to let this guy dangle right here. And I'm going to just go start up the engine, and we're going to make sure that this was a good repair. Okay, guys, I'm in the truck here, just waiting for the glow plug cycle to conclude, and then we'll give her a crank. Starts right up. Perfect. No codes on the engine, no problem with RPM, runs just fine, which is what I'd expect. Gonna let it run here just for a couple of moments here just to see if we get any kind of codes or anything. I don't expect there to be any, but just giving it a few minutes and everything's still running good. So guys, there you go. It is possible to rebuild one of these without destroying it. Depends on the particular type of failure that you have going on. So let's just review one more time to close the video. What are the failure points? Well, the failure points are these transistors, the fasteners that hold them in can come loose. They can come loose, and then with all the cycling, you can end up getting the solder connections on the board with the base and the emitter of these transistors, and you end up having a break in the connection. Getting these guys loose can also break the thermal connection that they have to this built-in heatsink, and they can fail that way. They can also fail because we get the potting material flexing with thermal contractions and expansion, and we get a break in the solder joints of that transistor that way as well. So everything that this rebuild takes care of is related to these two transistors and the multiple failure points they might have. I still strongly recommend bumper mounting. Even with this, it's still going to fail. Like I said at the beginning of the video, I never get more than 3.5 years out of these, even in a bumper mounted position. But hopefully this way I'm not plunking down $180, $185 every time one of these goes out. So if you got questions, guys, leave them below. If you got another technique for approaching this kind of a rebuild, let me know that too. And if you found this video useful or it saved you some money, hit that like button, hit that thanks button, and thanks for watching.